This media was gratuitously produced by Clear Contributions Audio and Video. The intellectual property contained within belongs to Dr. Barbara Van Kyken. Clear Contributions. Let's have clarity.
We'll go over these things, check your work. This is page 67. All right. All right, this is going to take me a minute to work through it.
Everything is twisted this way. Twisted 90 degrees. Other than that, it's exactly the same. I guess you have to show one, so it's not the same. Because you have to twist it.
See, it's hard for me, but now that I twist it, like, oh, everything is land, it goes one way, H2, see. Anyways, yeah, I didn't rotate it.
1, 2, 3, 4. Switch these. 4 and 1. So this one's S. 3, 4, 2, 1. This one's S, so I think B is identical, unless I'm going too fast. Are we in agreement?
No, but I probably just got it wrong.
Which one is where do you have the issue with the labeling or of each chirality center, or with deciding whether they're identical or enantiomers or whatever?
Saying the spin on it. That's the problem.
The R and S. Are you having problems with the priorities?
Nope.
Okay. Are you confused with putting the number 4 on the hatched line?
Yep.
Okay, we got it figured out. Number 4 has to be on the hatch line for perspective formula. So this one is an enantiomer. You can see it right off just because it's drawn as mirror images. But if you did the R and S to be safe, no, wait. Yeah. If they're mirror images, then they're enantiomers. The only two possibilities you can have for one chirality center is identical or enantiomers. They have to be mirror images of each other or the same. There are no other options. Are we in agreement with C? Any questions?
Go back to
Yeah, you can go back to B.
Sure.
Why is the CH3 a number 1 priority?
It's number 4, but I crossed it out and switched it with a number 1 to put it on the hatched line.
But on the right, you have it as a number 1.
The H3C instead of the C.
Aha.
Okay.
Like I said, going too fast. Let's see, I'll renumber this. So this is 4.
So then it would become
2, 4. Oh, that's why, because I was just looking back at what I had just crossed off, huh? That's what confused me. Okay, so this is 1, 3. Put 4 on the hatch line. 1, 2, 3. It's S, that's R. So they are enantiomers. Is that right? Okay. told you I might be going too fast. Oh, I'm sorry. Yes, yes, yes.
Wait, I have a question.
Okay.
You switched to 3 with the 4.
Uh-huh.
So then shouldn't it go like this? And then since...
So you ignore the 4 because it's in the very back, and so you're just bypassing it. So all you're doing is going 1, 2, 3.
Right.
Every
and then
time.
That's when you switched it though.
Uh-huh.
So then you cross that out and then you'd have to be in...
The opposite.
Oh, yeah. Okay.
Yeah.
Yeah. It just threw me off with that one over there that this one was going clockwise and was labeled S, so that's why I was thinking that way was S. Okay, now I get you now. Sorry, there we go.
Better. Okay.
Awesome.
Yes, ma'am. Oh, perfect. Terrific. Thank you. Okay. Oh, it's an eclipse on my paper. What did it do that for? Okay, so here's 1 and 4. I'm going to label them over here now before I do any switching around, just in case. Okay, then you have 1, 1, 8, and 1, 8, 8. The third number doesn't decide it, but the second number does. 2 and 3. 2, 3. You don't want 4 on the horizontal, that's horrible, so I've got to switch it with something. It doesn't matter which vertical one you switch it with. So originally it was S. This is S, so those are identical. Are we in agreement? Any questions about that one? Yes?
I label them correctly, but then I get confused once I switch the arrow. Should I just first do an R and then...
So you're only going to switch the arrow if you have to switch the number 4 priority into a better place to determine the stereochemistry. So here I had to switch it to put it on the vertical, but here I didn't. And so that's why this one I had to switch the designation at the end. This one I didn't. Okay. Anytime you switch 2 groups, it's the opposite of what you thought.
And because they're S and S like that.
That's right. Okay.
The Fisher projection is not as confusing as the perspective one.
Really?
Because, I don't know, I just see it like, I know bad, 4 is bad on the horizontal, I have to go 4, but when it's Fisher, when perspective, it gets...
It just has to be on that hatched line, going away.
Yeah.
All right. Oh, hallelujah. This one is not going to require a lot of layers. 1, 2, 3, 4. Okay, 4's on the horizontal again. So this one is R. This one is S. So these are enantiomers. Just like in class when you built the 2 that were mirror images of each other and you couldn't superimpose them, that's the only option you have for one chirality center. Are we in agreement with this one? And I might have already, no, okay. We already worked that next one. With two chirality centers, you can just look at it and decide if you have a mirror in between them or not. The only trick that you have to watch for here is if these two groups are the same, then you might have a meso compound, in which case it might look like you have a mirror image, but really they're identical. That's the only issue you got to watch out for with this. But otherwise, since this doesn't have that situation, it does look like they're mirror images of each other, so those are enantiomers. You can, This is G. You can go through and label R and S for each chirality center to make sure, but I think that you're going to tend to make more mistakes doing that than just looking at it. Any questions about this one? Go ahead.
One more time. How we pay attention if it's a meso compound?
Yes, if it's a meso compound, then the mirror image will actually be identical, because remember with a Fisher projection where you have two chirality centers, you can rotate 180 degrees of the plane of the paper. So it might look like it's a mirror image, but when you rotate it, it'll line up and be the same if it's meso.
Yeah. Okay, so then, because I did the R and S and I got it confused with identical.
This one is a meso compound, and so therefore, although it looks like a mirror image, when you rotate it, it's going to line up, so these are identical. If you rotate this whole thing 180 degrees, it'll line up. Okay. We did I, and now I'm on J. The one is cis and the other's trans. Since these are planar, you can also just rotate them on paper or flip them around. You can do anything with these. You can tell that they're not mirror images of each other, and you can also see that they're not the same. So those are diastereomers. You will never have enantiomers with an alkene, because the mirror image will be superimposable. So you can't have diastereomers with one chirality center. You can't have enantiomers with an alkene. With cyclic compounds, once again, you can do R and S, but what might be easier is just to move things around on paper or flip them around to see if they line up. For instance, these two here, if you just move, this one here is a meso compound. So it doesn't, and this is also meso, so that means they have to be identical. If you took this one and flipped it around, the two CLs would be going down and you could superimpose it. So those are identical.
So you can bond rotate on those ones.
You can't bond rotate, but what I'm doing is twisting the whole molecule, rotating the whole molecule 180 degrees.
Then wouldn't it be at the top though?
Right. So that's what I'm saying. If these CLs are on the bottom and I rotate the whole molecule, then it'll be on top. I'm flipping the whole molecule around.
Oh, I got it.
So I'm doing- Oh, you took your thing apart. We had a chemical reaction. Ooh. Yeah, what I'm doing is I'm just going whoop, the whole thing. Yeah.
But if they're meso, both of them, that means they're
You don't push that
identical.
close button. You gotta, Dr. B,
Yeah.
you gotta, we can't see it.
Well, I don't know what it wants me to do because I don't have anything here.
The remote just
What am I
Push
doing?
the side button. Push the side button.
Close button.
There you go.
That's a really weird voice. Yeah, so your clue is it's meso, then therefore since both of them are meso, they have to be identical.
So do I have this point right? Like, it's not that one's going up and one's going down, like they're both going like this, and you have to write it like that?
It's like they're both doing this.
So one's going down and the other's going up like this?
It's like if this was your two hydrogens. They're both going down, and the ring is actually a plane that you're looking at, a rough plane. So this up and down really does mean up and down. It's not like a Fisher projection where they're going away from you or something. Actually, they're coming somewhat towards you.
Okay. So is the chlorine also coming towards me as well?
Yep, they both are.
It's just one is angled up and one's angled down?
That's right.
Okay, that's it.
It's kind of like this. And it's going to be a little bit plainer to see if I have a 5-membered ring, because that's a lot more plainer. 6-membered rings are kind of puckered a little bit. But we'll get into that next semester. Okay. I have different bond lengths going on here, but the chlorines are both up. They kind of come towards you a little bit. The hydrogens are both down. They're both coming towards you a little bit.
Right, okay, so nothing actually is going into the middle, like ever angled into the ring, so to speak.
Right.
And I think
Yeah,
that's
you
why-
don't have anything going into it like this or something.
I think that's why I got confused, because no matter how I rotated, there's still some going in and some going out.
Yeah.
Got it. That makes sense.
So just with the rings, flip them around.
Okay, that makes sense.
Let's see. Everybody else okay with that? Okay. This one, if you have the chlorine here and you flip it around, it would end up on this side. So those aren't superimposable. They are mirror images. For instance, if you took this and slid it underneath, that one, it's a mirror image. Those are identical. Or I'm sorry, enantiomers. Okay, I had something different set up for your homework for tonight, but it sounds like you're iffy enough that maybe you would benefit from practicing this again tonight. So I'll modify this homework assignment in favor of putting some more practice with identical enantiomers and diastereomers on page 102. There's a lot of practice. I guess I knew you were going to have issues with this. So we'll do 102 and 103.
Wait, that's not what it's labeled in.
Oh, shoot, that's right. They've renumbered for me.
What is the number?
It's problem number 4.
Okay.
53?
It's 53, and so it goes through 57, I think.
Yeah. Do you want to break the practice up, or do you want to do a whole bunch of practice tonight with this? Do you want to do the whole thing, or do you just want to do a couple pages tonight and a couple pages tomorrow night?
A couple pages if you're doing it tonight.
All right. 102, 103.
The first two pieces.
I'm sorry, which is 53 and 54. I'm going to be really excited when your workbook comes in and we all have the same numbers and everything.
You look at the page numbers on the workbook, and most of us tend to look at the page numbers on the side. You see the little corner that has the numbers.
Okay, yeah.
That's where the rest of us tend to look.
Okay,
That's why.
perfect.
Cause you can like scroll through on the side instead of like doing what you're
Yeah,
doing. Scrolling all
yeah,
the way.
like this.
So that's why the rest of us.
So I see, okay.
Oh, yeah.
All right, I'll be able to figure out what page I was just scrolling through by hand because I didn't know where I was going
Yeah.
to find these problems, but okay, now I see that that will be better to figuring out page number for you. Yeah, I will be assigning all those pages eventually, and so if you wanted to do all of them tonight, that's fine, and then you're ahead of the game. I'm also going to be giving you some homework on incorporating all of this. We only have a couple of items to go through today before we put it all together. And the couple of things we're going over aren't really new. They're just reiterating everything to make sure that you're clear. So I'm now on page, oh wait for it. I'm on page 21, it looks like. Is this true?
Yep, it is true.
All right, we're getting the hang of this technology stuff. One common issue that I see is after you learn cis, trans, R, S, E, Z, it becomes very confusing about which kind of labels are you applying for which situation. So I just want to make sure that you're really clear cut on this. When are the labels R and S going to be used? Chirality center. So if you see perspective formula or Fisher projection, then that's when you're going to use those. So I know this is lame, but go with me on this. I try really hard anyway. If you have chirality centers, RS, chirality centers. I'm trying. I'm in here swinging.
No?
Labels E and Z, we'll do cis and trans in a minute. E and Z are going to be used for what? Right, and notice that one. Alkenes. I'm trying.
Wait, what are you using?
Alkenes. Uh-huh.
But isn't it spelled with an S?
Oh, go with me, okay?
I'm just spelling it with a Z.
That's fine.
I get it wrong. If I spell it wrong, maybe it's just no. That's easy.
At least you have this stuck in your head. That's all I'm going for. Okay, cis and trans. There were two cases when you can use cis and trans.
Alkenes.
Alkenes when, under what conditions? Specific. Hydrogen, when you're describing one hydrogen on each phenylic carbon. That's the only one. And sometimes you can do that with cyclic compounds to describe a general feature of them.
And what was the other one?
Cyclic compounds or alkenes where you have one hydrogen on each. They're opposite.
On the same side, and the Z is the
They're on.
letter.
You have to have on two different carbons, and then you draw a line through the double bond. If the two hydrogens are on opposite sides of the line, it's E. If they're on the same side, it's Z. I was a student once, you know.
So what's the difference between cis and trans and Z?
So E and Z you can always use to describe the stereochemistry of an alkene if it has a unique type of stereochemistry to describe. Cis and trans you can only use when there's one hydrogen on each phenylic carbon. However, if you have one hydrogen on each phenylic carbon, you could use cis, trans, or EZ. And so in that case, cis correlates with Z and trans correlates with E. Good question. Okay, so this kind of roadmap that I gave you here, for naming a molecule. This chapter 2 has just been about step 5 for naming a molecule. I do have the directions here for if it's a Fisher projection, then you got to make sure that the number 4 priority is on a vertical line. If it's perspective formula, it's got to be on the hatched line, and when to use everything. So I've got all the rules right here. But now what I got to get you to do is incorporate step 5 with steps 1 through 4. So that's all we're going to do for the rest of the time. So first off is how do you include the information about stereochemistry? You put the stereochemistry designation at the very beginning of the name. So for instance, if you had this, and you're going through and you're finding the functional group and the parent hydrocarbon, and you're writing the name out, and so you have butene. And then you are saying if there's more than one of anything. There isn't, and you put the number in. Sorry, I jumped ahead there. I got so excited. Anyway, now you decided that this is either trans or E. Then you write that at the beginning. So E-butene, or you could alternatively do trans-butene, or sometimes the abbreviation T is used for trans.
Isn't E also trans though?
If you have one hydrogen on each vanillic carbon.
So then would you put both or just put trans?
One or the other.
Okay. Yeah. So really you don't need to know cis or trans unless it comes to cyclocompounds.
You do need to know cis and trans, though, because it's so commonly used, even though you're limited in when you can apply it.
Okay.
All right, then what do you need to do if there are multiple labels for stereochemistry? Let's say that there are multiple double bonds or there's multiple chirality centers. Then you have to write the number for where that stereochemistry designation applies. So if you had something like this, and you've got 2 double bonds like that. And this one is going to occur, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. All right, it just became a little bit longer. Okay, so this is on carbon 2, and that's on carbon 5. Then in front, you would write 2E5Z. So you have to write the location number for each type of stereochemistry that you've got in the list. Otherwise, it's not clear what stereochemistry label belongs where. This is going to be true even if the stereochemistry label is identical. Just like before, if you have 2 methyl groups attached to the same carbon of the parent hydrocarbon, you still have to put a number for each. If you have multiple chirality centers or multiple double bonds that have stereochemistry, you have to write a location number for each one.
So then you'd also have to write 2 and 5 for ene.
Right. And the reason I'm kind of jumping ahead here without working the whole problem is we're going to be working entire problems in a minute. I just want you to see once what I'm saying about what that means. Okay, so if you have multiple labels, put the location number for each. The 5 steps, you can fill this in. I want to get going on applying everything. I'm on page 25. I want to give you some guided practice so that then you can try and apply it.
On page 25.
I think so. Okay, so you see that I've got this with the 5 steps that you've learned so that you can go step by step and work through the problem, and this will help you refresh chapter 1 as well. All right, so if you're naming the molecule that's shown here, this only has 1 chirality center. This carbon has 2 methyl groups on it. So we're only naming this, or only having to worry about that chirality center. But I want you to get used to highlighting if you have things drawn as a Fisher projection or perspective formula. So remember, your first step was identify or locate everything. So you have the OH is a functional group. If you've gotten rusty, a nitrogen is also a functional group, and a double bond is also, or a triple bond is also a functional group. You need to find the longest continuous carbon chain that contains the carbon directly attached to the oxygen. So you can do that, or you could peel off and do the other methyl group. Doesn't matter, you'll come up with the same name. One thing that I want to make sure that you notice is that when I'm doing the substituents, the methyl group's a substituent, but the hydrogens are not. The hydrogens are just part of the parent hydrocarbon chain. These are just drawn off to the side to represent a particular stereochemistry, but don't highlight them as a substituent and try and include that in the name somehow.
Oh, crap.
It's just part of the parent hydrocarbon. All right, so you've got a methyl group. 1, 2, 3, 4, 5. Pentane. And an alcohol, so it has an all ending. And that means that, that means that I'm going to get rid of the E so you don't have the 2 vowels.
Am I crazy? Isn't that butane? Because there's 4 carbons, not.
I'm really glad you asked.
Does it imply?
This one that just went past, this is a carbon here for our chirality center. I'm glad you asked that one. That's an important question to clarify. Am I good to go on? Step 3, of course, is say if you have more than one of any particular substituent or functional group, and you don't, so we're going to just keep that same base name that you're working off of. And then step 4, you're going to number the parent hydrocarbon in each direction so that you give the lowest number possible to a carbon directly attached to a functional group, and you only worry about tiebreaker rules if there is a tie in numbering. You don't have a tie here, so the lowest number you can give to a carbon directly attached to the OH is the number 2. So that means that I'm going to use the numbering system that I did top to bottom here. Yeah. I have a little bit of a hard time seeing the colors here, but it might be the angle I'm at. Can you guys see colors okay? All right. So you have the number 4 in front of the methyl. And a 2 in front of the all.
And the YL is there because it's attached to a carbon.
That's right. It's not the...
What is changed to methyl?
Right. It's a substituent, not the parent hydrocarbon.
What?
It's a substituent, not the parent hydrocarbon. So if it was the parent hydrocarbon, like the 5-carbon unit we highlighted in blue, then it has an ane ending. If it's highlighted in green, it's got a YL ending. Because it's attached to the parent hydrocarbon. Okay, so that's where you are so far. I would recommend redrawing the molecule to figure out stereochemistry. In the book here or on test papers, I will try to draw a fresh copy because otherwise you got too many numbers. You've got all of these location numbers and then you're going to be doing priority numbers and it's going to be numbers on top of numbers on top of numbers. So try it with a fresh copy. Bless you. Are you okay with it being R, or am I jumping the gun here? All right, so now you just write the letter R out in front. If there were multiple chirality centers, you have to say that it's on carbon 2, and then the other ones you'd also have to give a number. But since there's only one, you just have to put the designation.
What about the second chirality center?
There isn't a second chirality center because this is 2 methyl groups.
Oh, I was about to ask how you label if there's 2 methyl groups. Oh.
If we did tell you it was 2R, would we get marked down points?
No. No, I'll probably be good-natured about it. Okay, so it's just a process. Just go through those 5 steps. The only place where I think you might get tangled up is the tiebreaker rules, especially for step 4. But otherwise, it's just going to be the same thing every time, every time. All right, now you got 2 chirality centers. I'm going to let you try and work through it a little bit instead of going step by step with you just to see how you're doing.
Just to make sure, there is no functional group on this, right?
Correct.
Okay, sure.
Good call.
So how do I show that both of them are R?
You have to write the location number. So you know how you numbered the parent hydrocarbon? Whatever number that is on the parent hydrocarbon, that's what you put for the stereochemistry.
They are both R, right?
No.
What? One of them's S. Oh, yeah, you're right. I didn't actually put it on my paper. Yeah, all the time. But if it's only one chiral symbol, you don't need to show it.
Right. Because it is an ambiguous. Yeah? Yes, ma'am. Yeah. I'll go through step by step. I was just making sure everybody got caught up. Okay.
Oh, it's doesn't matter if we say 2S before we say 3R. Oh, you're right.
It goes in numerical order.
Okay.
How do you know when we're supposed to put more than S or R?
So for instance, down for all of these, it's R and S, because those are all chirality centers. For this, it would be either cis and trans or E or Z.
So if you can label it using other names,
Then you do
go
that.
in the name.
It's very specific. Yeah, and it's going to be the same thing where it goes at the beginning of the name.
Okay.
Yep.
Wait.
All right. Since we're about out of time here, I'll go over this really quickly. You're okay with the root name being dibromopentane through step 3. Step 4, you're numbering the parent hydrocarbon in each direction, giving the lowest number possible to the carbon directly attached to the functional group. There is no functional group, so you go to the first tiebreaker rule, where you give the lowest number possible to a substituent. The best numbering direction then would be from top to bottom, the way that I've done it, because you have a 2-3 combination as opposed to 3-4. So 2 is the lowest number out of those. So that's the direction that you go. And so therefore, this chirality center is also 2. So whatever label you come up with for that, we put the 2 with that. It's the same numbering as for the parent hydrocarbon label. Did you get it? Almost. Oh, good. Huh?
So you switch to 3 and 4, and therefore this is going S, right?
That's
So
right.
Oh my god.
You see
It's
it?
gonna be the death of me, dude. I can never get which way R is. I always
Clockwise.
I told myself clockwise
Turning.
is R, counterclockwise is S, and I never seem to get it right. I mess it up every time.
Think about driving a car, then which way you're turning. What other last quick questions do you have where you messed up and you're not sure what happened there? You got this? Here's your homework for tonight. I've got a couple pages of doing this where you're labeling or writing the whole name for the molecule, and a couple pages where you're figuring out things that are enantiomers or diastereomers and such. And just a reminder, if it has a double bond and so you're labeling it E or Z, you got the same issue where you write it at the start of the name for the molecule. If there are multiple double bonds, then you have to say the location also that corresponds to each, even if they're the same label. Good, this is your first go around with putting it together, so I'm really glad how well you're doing. We'll practice it a little bit more, but it's going to be the same 5 things every time, so you're going to get to the point where it's just second nature. It's going to be great. All right.
Thank you.
Later.